Welcome to the GEM files. This is the vault of broken physics, case number 08. Why is gravity so weak? Gravity is the invisible hand that shapes our entire universe. And yet, when we zoom in and observe it at the microscopic scale, something completely bizarre happens. To really grasp the scale of this anomaly, let's look at a visceral, everyday paradox. A tiny refrigerator magnet can lift a paperclip against the gravitational pull of the entire Earth. Just think about that for a second. You've got an entire planet, billions of trillions of tons of rock and iron, generating a field strong enough to hold the moon in orbit, pulling down on that clip. And yet a little piece of magnetized metal the size of a coin just casually reaches down, snaps the paperclip upward, and completely wins the tug-of-war. A pocket magnet can defeat a planet. Honestly, that should bother you. It certainly bothers physicists, because what seems like a simple parlor trick is actually a glaring stress fracture in our understanding of modern physics. It's a visceral reminder that the forces of nature are absolutely not operating on the same scale, not by a long shot. Down at the local level, gravity is fundamentally outmatched by electromagnetism. We need to understand that gravity isn't just a little bit weaker here. It is fantastically weaker. We are talking about orders of magnitude that literally boggle the mind. On one hand, we have these highly concentrated local accounts, right? Things like the strong nuclear force holding atoms together, and the electroweak scale, where the famous Higgs boson lives. But on the other hand, we have gravity, which only finally becomes strong at this incredibly distant, high-energy boundary we call the Planck scale. So why is there such an enormous separation? Why does the Higgs mass remain so incredibly far below the Planck scale? The universe is an incredibly energetic place, and yet it doesn't pull the local particle scale upward to match gravity's ultimate scale. The numbers just do not sit comfortably in the same ledger. When we sit down and try to write out the equations for all these forces on a single sheet of paper, the math practically screams at us that something is structurally unbalanced. And that brings us to our forensic investigation for today. We are officially opening case number 08. In this explainer, we're stepping into a slightly more ominous, highly analytical space. We're going to look at the universe not just as a random collection of isolated forces, but as a deep system of continuous emergence and coherence. Now, I want to be absolutely clear about something. Modern physics is not broken, but it does have stress fractures. We aren't here to reject the standard models that built our modern world. Those models are incredibly powerful and undeniably successful, but they are structurally incomplete. So today, we're acting as forensic investigators, probing the places where the math works beautifully, but the underlying architecture feels like it's missing a massive fundamental load-bearing pillar. Let's take a look at the standard search so far. Physicists have explored some truly brilliant ways to explain this hierarchy. Maybe there's a hidden supersymmetry protecting the Higgs mass from skyrocketing. Or perhaps there are extra hidden dimensions, branes, that dilute gravity, letting it leak away so it merely appears weak to us. Maybe there are new undiscovered particles. Or perhaps the universe is simply fine-tuned in a way we just don't grasp yet. Now, these are serious, mathematically rigorous attempts to resolve a profound problem. But what if they are brilliant answers to the wrong fundamental question? This is where we make a massive pivot. The question might not be why gravity failed to match the other forces. The question might be whether gravity even belongs in the same conceptual category to begin with. This is the core insight of general emergence mechanics, or GEM. What if our entire baseline assumption that gravity is a local interaction, just like electromagnetism or the strong and weak forces, what if that is actually a category error? Think of it like forensic accounting. The other forces, electromagnetism, the strong force, the weak force, these are concentrated, local transactions. They're specific, high-intensity interactions isolated within the field. But gravity? Gravity is completely different. It isn't a specific transaction at all. Gravity is the baseline ledger itself. It's the field-wide accounting system spanning the entire universe. So when you compare a local nuclear force to gravity, you're basically comparing a single concentrated deposit to the background architecture of the entire banking system. So let's introduce the core physics of GEM. We have this concept called persistence depth, represented by the letter D. In this framework, the universe is modeled as a coherence field that intrinsically wants to persist, to remain stable. Persistence depth is essentially the baseline geometry of this field. It modulates how things propagate locally and how stiff the local field is. Viewed this way, gravity isn't some weak, leaky force pulling on particles. Gravity emerges as a depth gradient behavior. It is literally the residual geometric slope of the field itself.
So, what does this mean for what we actually observe? Well, in the mathematics of a depth monotone gem cosmology, the gravitational constant g is inversely proportional to this persistence depth. G scales as d to the minus 1. This implies that as our universe evolves and its persistence depth increases, as it settles into a more relaxed, deeper baseline state, effective constants can undergo a correlated drift. So a shallower early universe might have had a stronger effective gravity, while our mature late-stage universe experiences gravity as a wide, deeply relaxed baseline geometry.
You might be wondering, how does this actually create the gravity we feel pulling us down right now? The mechanism is beautifully elegant. First, incredibly fast microscopic vibrations in the background environment smooths themselves out, leaving behind a stable, coarse-grained field. Second, as energy moves through this environment, its speed and behavior are recalibrated. Think of it kind of like light slowing down as it enters water. And finally, variations in that persistence depth act like a cosmic refractive index. Matter naturally bends toward the deeper, more relaxed regions of the field. That bending, playing out across the vast geometry of space, is exactly what we experience as Newtonian gravitational attraction.
Which brings us to a truly profound realization. Gravity is not weak because it's leaking away into extra dimensions. It is weak because it belongs to the whole field. Down at the microscopic particle scale, gravity appears fantastically weak simply because it was never designed to operate as a local concentrated particle account. Its strength is entirely distributed across the vast macroscopic expanse of the universe.
The other forces write local accounts. Gravity keeps the ledger. Reframing it this way solves the conceptual category error of the hierarchy problem. Gravity carries the residual, geometric weight left over after all the highly concentrated local particle transactions have balanced their books. It's not a missing local strength. It is a depth-dependent baseline geometry. So the hierarchy problem isn't necessarily proof that modern physics is collapsing. It's more like a warning light on the dashboard of our perspective. Is gravity truly weak, or have we been trying to force it into the wrong box for nearly a century, comparing the vast emergent baseline of the whole field to a local transaction? Once you stop seeing gravity as a failed, weak force and start seeing it as the foundational ledger of space itself, well, the universe starts to look very, very different.